So we're going to try a new setup here for section 10.2 on limits and continuity. First of all, what we're going to see is that continuity, the old definition back in the 80s when I was studying originally, we were told, because we did most of our graphs, we drew them by hand, that continuity is basically you put down your pencil and you're able to draw the graph without lifting your pen or pencil. If we needed to lift the pencil and jump it up, that's what we call discontinuity. And so we're going to build that with an understanding of what we've got so far from limits, and we're going to take a look at what is continuity. So to kind of understand continuity, we look at discontinuities. What does it mean to be discontinuous? Well, we've got an example graph down here. You can read through the part of the textbook, but basically we see here when x is 0, we get this sort of jump where the graph was coming down towards -1. So we would have said the limit was going towards -1. We would have written the limit as x goes to 0 from the left is equal to -1. And then, but what happens itself, the function value we can see is up here at 1, 2, 3. So the function value at 0 is equal to 3, as well as the limit from the right-hand side is going to be 3. So the limit as x goes to 0 from the right, that's equal to 3. So the limits are not equal. There is a function value, but the limits aren't equal. This other point, when we look at 1, we can kind of see what happens here is that the limit actually does exist because we're going closer to a y value of +1 from the left and +1 from the right. So the limit exists. The limit's actually equal to 1, but the function value has a different value. The function value would be 2 here. So the function value at 1 equals 2, but the limit as x goes to 1 is equal to 1. And again, I should have an f of x in here, and we'll do that. Okay? So this is discontinuous. So continuity would be the opposite of that. There's no places that look like this. So now let's go ahead and take a look at the definition itself of what actually continuity is. So continuity has two parts. As we said, the limit has to exist. There has to be, the left and right limits have to be the same for the limit to exist. Okay, so that's one thing that has to happen. And then the other thing is that limit actually has to be equal to the function value. So there has to be a function value at that point that is equal to the limit. Two things have to happen. If either one of those does not happen, either A or B does not occur, A does not occur but B does, B doesn't occur but A does, then we have something called discontinuity. Okay, one or the other. So either the limit as x goes to that point, that value, x goes to A, does not exist, so that's going to cause a discontinuity, or their limit exists, but it's not the same as the function value. Now, one of those discontinuities we'll be able to fix if we were to basically move the function value down to the right spot. This is sort of what we're going to look at. This here is fixable. But when the limits don't exist, it's not fixable because you'd have to really reconstruct the whole function. But for the second part, you moved a point. Okay. We just need to move a point. So let's look at a few examples here. Is this continuous on its domain or not continuous? Take a look, think about it for a moment. What do you say? Is it continuous or not? According to does the limit at each of these points occur? Yeah, limit from the left and the right looks like it's going to be the same. Function values are the same. So what we see here, you should think through it. That yes, it is continuous on its domain. Now, obviously, there's no graph over here, so there's no domain. So the domain goes from -1 to infinity, and we're going to get a smooth, continuous function going on here. Okay. How about this one? Is it continuous on its domain or not continuous on its domain? This part, we're looking pretty good. You can see each point, the limit from the left and the right would be the same. And of course, so it's a nice smooth function. It's nice continuous. What about here at 2? Well, the limit from this, the limit over here, the limit from the left is going to a y value of 0. The limit from the right is going towards 1. So 1 and 0 are not the same. The limits are not the same. And that's one of the things that's required of these, is the limits have to be the same. Okay. So this would not be continuous on its domain. I'd say that would be B. Erase that, go there. B. B is the correct answer. Now, this is very similar, and I'll be honest, it was a little, it threw me a little bit. Okay, how about you? Continuous on its domain or not continuous on its domain? You want to jump in and say it's not continuous, right? But the key part is on its domain. So the question here is 2 in the domain of this function. Well, 2, if you plug in 2, it's undefined here, it's undefined. It is not defined. This function is not defined at x equals 2. 2 is not in its domain. So if you just look at its domain, it is continuous on its domain. A little tricky, but let's go back. A, right? It is continuous on its domain. So what we've done is we've also looked at that there's kind of 2 types of breaks from those examples. There's one, the first one we looked at, the domain includes the point of discontinuity, right? So here at x equals 2, we get a discontinuity because this value of 2, x equals 2, is in the domain. Okay. Over on the left side, we get what's called a singularity because it's a break in the graph, but it's not a discontinuity because that point is not, that x value is not in the domain. Okay, so it's a kind of a technical side. Singularity is a break where that point's not in the domain. And we see that like 1 over x, yeah? 1 over x. We'll look at some other examples too. 1 over x, we always say, well, x not equal to 0 because that gives an undefined part. So we would get a singularity at 0, not a discontinuity. Limit doesn't exist either, but you would not have a discontinuity at 0. You get a singularity. Okay, so that's pretty much it for the instructional side of things. Let's start taking a look at a few examples. Is this continuous or not? Now, one of the things we saw here is that, functions like x plus 3, is there any place it would be undefined? Think about it. Well, no, we're not going to divide by x, so we're not going to get some 0. Same thing with 5 minus x. These typically will be continuous, but on a piecewise function, where would the possible discontinuities occur? They'll occur here where the domain changes. Okay, the domain changes, not the main. It writes down everything I say. So what we need to do is we just need to check what happens at x equals 1. So if this top value ends up being the same as where plugging in 1 here, even though 1 is not in the domain, it would show us that these limits, that the limit as 5 minus x was going to 1 from the left matched up here. Basically, if these two are the same, then we're okay. We are continuous. And that's what I mean by okay. So let's plug in 1 to this top function. So we go x plus 3 with plugging in x equals 1. So that gives us 1 plus 3 equals 4. So now it will be continuous as long as this next piece, when I plug in 1, is 4 as well, because then that's where it's going to take off from, right? Because it's going to be continuous everywhere else. So then I get 5. I'll just jump to it. X is equal to 1. Now again, that's not really in the domain, but it's a quick way to do a check. And as we saw with these, as long as it's continuous elsewhere, we can get the limit by plugging it in. So 5 minus 1 is also 4. So if we were to look at this graph, we would see at x equals 1, we would have a value of 4. So x plus 3 would be coming into it. Let's see if we can. It's always hard to draw graphs for these, but you could take a look. Okay, so we get 1. This top one says it's actually equal. X plus 3 is an increasing function. Y-intercept's at 3, so actually it's not too hard. It would be a line going like this. Okay. This 5 minus x has a negative slope, so it's going down. It would have, if I went the other way, it would have a y-intercept of 5, so it's the line that would go up this way. Again, it's got an open circle, but then it's also from this point, if I were to come down this way, it would be the line that looked like that. Okay, so we see it's continuous because the limits are both going to 4 on both sides, and it's connected. It's continuous, yes. So that's one question. There'll be some in the homework like that. Let's clear that out. Let's move to the next question, which it's different. It's a different question, same place, okay? So now, again, with this, what we want to do is we've got this piecewise function. We want to check at the place. If it was going to be discontinuous, it will happen here. This is where the jump would occur. So again, we plug in 1 to each of these functions. So I'm going to plug in x plus 3. I'm going to do 1 plus 3. And that's going to give me 4. And for the bottom one, I'm going to do 1 minus 1. Again, looking at this point, even though 1 is not included here, because if we understand that this is continuous everywhere else, the limit as it gets close to 1 should be very close there. Okay. 1 minus 1 is 0. 4 and 0 are not equal. 4 does not equal 0. The limits, what we've got is, if we graph these two, and we're at 1, x plus 3 is a line going up. It's got a y-intercept of 3. 1, 2, 3. And then it's going to go up. So it's, the first part is a line like this. So there's our 4, right? But the second line is is going down and has a y-intercept of 1. So it would actually be starting here and going down this way. So you can see the discontinuity there. So this is not continuous. Okay. You'll have some in the homework that are similar to this, and it will give you piecewise functions. The place you need to check is these overlaps. If there were more than one overlap, you check more than one place. You check wherever there's this overlap. Okay, so let's come back here. We'll clear off the screen. Let's move forward. With these problems, we're going to do a little bit different. This, again, comes directly out of the homework. I'm using some different examples. Actually, these examples are in the textbook. So if you want to look at the textbook, they'll show you how they do it. And then you've got some homework problems with this exact, what I did is it's a hybrid. I took the description of the problem from the homework. I took the functions that they're using from the examples in the textbook. Okay, so use a graph of f or some other method to determine what, if any, value to assign to f of a to make f continuous at a. So what you see here is that a equals 2. If we plug that in, we get an undefined function, right? Plug in 2. 2 minus 2 is 0. You get division by 0, and it's undefined. You plug 2 up here, you get 8. So actually you get what they call indeterminate form, because you actually get 0 over 0. But you don't get a function value. Okay. So what we're going to do is we're going to graph it, and we're going to see what happens about there. And then we're going to see, what if I were to sort of make this a piecewise function? Everywhere except a equals 2, the function f of x is such. But as soon as x equals 2, I will give it a value, and can I make it continuous? Okay, so let's, I'm going to use Desmos because it's a good application to use for showing what's going on. Yeah, so I really should put parentheses like that, and then we've got x minus 2. It looks like a parabola, and if you remember x cubed minus 8 is a difference of cubes, it'll factor out into an x minus 2, and that's why we get those canceling. But what we want to see is what happens when x is 2. This is the other reason I like Desmos. You can just drag it down. So when x is 2, look, it's happening. I can click here. As I get close to 2, at 2 it is undefined. So there is actually a hole there, and you can kind of see the value is open, isn't it? If I can move off it, and then I move off and I get closed. So as I get close to 2, again, another thing I like about Desmos, I can kind of think of this as a limit. So I let x get closer and closer to 2, y is getting closer to 12. And it looks like when I get to 2, right, so it's very close to 12, it's undefined, it's an open circle. What if I just said, well, whenever x is equal to 2, let's make y equal to 12? That would plug the hole. And notice on the other side, as I get close to 2 from the other side, it's also getting close to 12. So my answer over here is that we are going to let what would make it continuous at that point is if we make f of 2 equal to 12. 12 is the number. And I think in the homework, you just need to enter the number. Okay. So really what we want is we want a piecewise function, f of x. And I guess you could do it either way. When x equals 2, your value should be 12. And when x is not equal to 2, that means everywhere else it's equal to this x to the third minus 8 over x minus 2. Okay, so that's that's the piecewise function we would actually define. For the homework answer, you just need to say that the function value should be 12. Okay. Let's take a look at this one, and then we'll look at one more. But again, we're going to do this graphically. So we will, yeah, when I'm looking over there, I've got a monitor. I'm trying to fool you to think I only have one thing going on, but we'll see. So A is a place we can see when I plug in A equal to 0. When I plug in 0, it's not going to be happy here. It's actually, I get a 0 in the denominator. I'll get a e to the 0, which is 1, 1 minus 1. I also get a indiscriminate form. Indiscriminate form. That's not right. I get something that's undefined. Oh, I didn't realize. I forgot. I shouldn't be blocking my closed captioning. So again, it's my first shot through with it. Let me know what you think. We can't improve unless we try something new. E to the 2x come down minus 1. So make sure the minus 1's not up in the exponent, and then divided by x. Okay. And so on this one, we want to see what happens at 0. And hey, it looks like it's continuous there. But watch, if we click on this, we get solids and we get values as we're getting closer to 0. It looks like we're getting closer to 2. But watch, when we get exactly to 0, see, it's getting there. We get exact, see if I can get there. Getting close to 2 is negative 0.01, 1.98. If I can just get one more step there. At 0, it's actually undefined, and it shows the open circle. Okay, so there's a hole in this graph. If when x is 0, I just let the function be equal to 2, I've plugged that hole. That's all there is. And I see on the other side, as I sort of come close to 0 from the right side, I'm also getting closer and closer to 2. So the limits are there. It fits the description now. All I need to do is make it so that when the function value, when f of 0, when I plug in 0 to the function, that I have to define it, it's equal to 2. Now I plug the hole. And again, we get this piecewise function. Let's see if I can kind of go like this. So this would be the function everywhere a is actually not equal to 0. When a equals 0, actually, I guess we want to define it with x. So I'll put an x here. When x equals not 1, but 0, we want to say that the function needs to be 2. And again, for this one, if it was, it's in the textbook, it's not in the homework, but that's what you want it to be. You want the function value to be 2. One more example, and then you're ready to do, there's only 6 homework problems in this one. Maybe you looked at it and already did it. Okay, so this one is a little different because it's got the absolute value. And oops, I didn't want that. Come back. So let's see the graph of this one. And again, as I don't think you have any of these with the absolute value in the homework, but there is a way to graph absolute value on, there's a function both in the TI-84 calculator and in the Casio calculators, and I'll help you with those later. What I try to make the lecture videos about is just the concepts. And so that's why I use Desmos as a little bit easier tool to work with to look at concepts. In class, I'll be happy to bring up either calculator that you might want to see it with. And when we get to things that have some especially difficult things, make a few videos of using the graphing calculators. Okay, so I want the function absolute value of x. I think it's just ABS of x divided by x. And that's our function. And what we see happening when x gets to be 0, notice 0 basically is 0 over 0, again, another indeterminate form. I think that might be correct. But notice the limit here from the left side is going towards -1. It's undefined at 0. Let's see. Actually, I don't even know where to go. But if I, because 0 is actually not in the domain. 0 is undefined. So 0 is not in the domain. But from the other side, my limit is +1. So these limits, there's no way to match up -1 with 1. I can't make a big point, I can't just come over here and say, oh, let's make this work. Let's make a huge point here and go, they're connected now. No, that's not a point. Okay, so this is one case where we have to say basically it does not exist. Okay, so in this case, in the homework, if we had something like that, we would answer with none. We can't make it work. So when there's a gap, you can't do it. When there's kind of a flow and just a one little point hole, we can fill that 1 point hole. But that's all the power we have, nothing else. Okay, so let's clear this. Let's click on this. And I always like to click one more last time. I'm pretty sure that that's the last slide I have. And we've looped back to the beginning. So that's section 10.2, limits and continuity. I'm going to process this through, get it posted in the course, and I look forward to any feedback, whether the captioning was helpful or not. It's something that really we should be doing all the time so that everyone can take advantage of the recorded lectures. So be well, stay safe, keep making your progress, and we'll be in touch in class Wednesday morning.